Activity 4, Intro, the Electromag. Is that permanent magnets get their magnetism, their magnetic field, from the collective common spin rotation of electrons about their axes, within magnetic domains that of course only exist in iron, nickel, steel, cobalt, and other rare earth metals like neodymium. Electromags, how they are different is they get their magnetic fields from the flow of electrons. Okay, so it just basically needs to be an electric circuit. You just need current. And you have a magnetic field. This means that any circuit that you built in the past, like in the electricity unit, has been an electromagnet. There's been a magnetic field surrounding that circuit, and you probably didn't even know it. At minimum, bare minimum, to make an electromagnet, all you need is a very, very basic circuit. Okay, like an energy source, battery, and some wire. Okay, some basic wire. And as soon as you connect the two, you have electrons flowing through the wire, you have current, and there's actually a magnetic field around this wire. Can it really do anything? No, it's really, really weak. A straight current carrying wire, if you have current flowing through a wire, you get a magnetic field around that wire. So how do you make this stronger? Coil it, and that's called a solenoid. As soon as I connect that, zoink! All right, now I have an even stronger magnetic field. Is it strong enough to do anything? Still really not. It's pretty weak. You have a magnetic field that looks something like this. So how could we make this stronger? Well, I'll tell you what. Add a permanent magnet in combination with the electromagnet. Make what's called now an iron core solenoid. Like an iron nail in the middle of it. You wrap the wire around the nail. This is strong enough that it can actually do something. The magnetic field of the solenoid then magnetizes the iron nail. It causes its electrons to start spinning in common directions, and the magnetic domains start to line up, and the magnetic field of the solenoid then magnetizes the iron nail. It generates a magnetic field, and the two magnetic fields combine to make one that's strong enough to do something. Be testing the effect of number of wraps and voltage, or number of batteries, on the strength of the electromagnet of the iron core solenoid. All right, people, so we are testing the effect of two different independent variables on one dependent variable. So to do that properly, of course, you guys know, as you test the effect of one of those independent variables, you have to keep the other independent variable constant. Okay, so you were testing, or we were trying to conclude on the effect of number of wraps on magnetic strength, okay, while holding voltage constant. And then you tested the effect of voltage on magnetic strength while holding the number of wraps constant. So to stay organized and to really be able to conclude on the effect of one variable on another, you have to hold the other variables constant, right? That's experiment design. So say, for example, as you're testing the number of wraps, the effect of number of wraps on magnetic field strength, as you increase the number of wraps, test how much stronger it becomes while holding the number of batteries or the voltage constant. So as I test, okay, and then increase the number of wraps further, okay, test again, increase the number of wraps further, test again, okay, I'm changing the number of wraps, all right, while keeping the voltage constant, right? And then as you test the effect of voltage on magnet strength, you want to keep the number of wraps constant. 2 batteries, test, 2, 3 batteries, same number of wraps, test, 4 batteries, which we didn't do, okay, test. All right, so I'm changing the voltage but keeping the number of wraps constant. All right, and what you should have found in your data is that, well, if we represented this with graphically, we would have to have two graphs, right? Because we have two independent variables and you can't graph two independent variables on one graph. All right, so one graph would look something like this. Effect of number of wraps on strength. Okay, so number of wraps is on the x, that's the independent. Strength is our dependent, so that would go on the y. How is the strength quantified in this example? Well, it was quantified by the number of baby nails that were picked up. So we can essentially replace strength with number of baby nails picked up. If you were to graph or plot that data, it's going to be a direct relationship. As the number of wraps increases, the number of baby nails picked up increases. The other graph, the effect of voltage on number of baby nails. Our independent variable this time is voltage. Our dependent variable on the y remains number of baby nails. If you were to plot that data, it's the same kind of relationship. It's the same kind of direct relationship. You get something that looks like that. Again, as the voltage increases, the number of baby nails picked up, and therefore the magnetic strength increases. So they're both direct relationships. So if you were to try and make the strongest electromagnet possible, you would maximize number of wraps. And what about the voltage? You would maximize it as well. The more wraps you have, the more voltage you have, the stronger the electromagnet. So as the number of wraps increases and the voltage increases, the strength increases.